Good morning class and welcome to our continuing discussion on energy storage systems and technologies. So today we will continue our discussion on different types of electrochemical energy storage systems, specifically different types of batteries that are used for various energy storage applications. And today we will, in the last class we discussed two types of battery systems, the lead oxide based energy storage system and nickel cadmium based battery systems. Today we will look at a variant of the nickel based battery system where cadmium has been removed, because as we discussed in the previous lecture, cadmium is a toxic metal and is harmful to human health and the environment. So there is a push to replace cadmium with some environment friendly metal while keeping the advantages of a nickel cadmium battery intact. So to that end, a new type of battery is being used nowadays, which is called nickel metal hydride battery. So in the nickel metal hydride battery, the negative electrode is a complex metal mixture that is attached to a perforated sheet. So instead of a single metal, it's a complex kind of a mixture of multiple metals. And the metal mixture is made up of lanthanum, rubidium, nickel, cobalt and silicon in this molar ratio. So 0.8 moles of lanthanum, 0.2 moles of rubidium, 2.5 moles of nickel, 2.4 moles of cobalt, 0.1 moles of silicon. This complex metal mixture is attached to a perforated sheet and this is acting as our negative electrode. Okay. In the positive electrode side, we still have the nickel oxyhydroxide battery material that was used for the nickel cadmium based battery. Here we are also getting an EMF of around 1.2 volts, but a much higher cycle life of 1000 cycles. So if you remember, the nickel cadmium battery lasted only 200 to 300 cycles. This one lasts to around 1000 cycle life. And the specific energy density is around 80 watt hour per kg. Okay. So it has a reasonably good energy density as well. So remember, the nickel battery, nickel cadmium battery was around 50-60 watt hours per kg. The lead battery was around 40 watt hours per kg, can go down to 20 watt hours per kg at high power loads. Here we are getting an energy density of 80 watt hour per kg. So you are able to store more energy for the same mass of battery. Again, the use is in portable electronic and user equipment like remote controls, electric shavers, portable audio and video systems. And the electrolyte once again is the 20% potassium hydroxide solution immobilized in organic fleas. So the positive electrode remains the same, the electrolyte and separator remains the same, only the anode metal has changed from cadmium to this metal mixture. Okay. And we will discuss this metal mixture as a as ME, this metal mixture. Okay. So in the negative electrode, during the discharge reaction, a hydride of this metal mixture. So this metal hydride is there in the negative electrode, and this metal hydride reacts with the OH minus ions coming from the electrolyte, which is a KOH electrolyte. So OH minus ions are formed, which is traveling to the negative electrode during the discharge process, and it is reacting with the metal hydride that is present in the electrode to produce pure metal, water and 1 mole of electron, which is being sent to the external circuit. The positive electrode contains nickel oxyhydroxide. Again, the reaction remains the same, plus water plus electron going to nickel hydroxide plus OH minus. So again we have a transport of OH minus ions from the positive electrode side to the negative electrode side during the discharge process. And of course, when the battery is recharging, the direction of the ionic and the electron transport is opposite and the reactions are exactly reversed. So the overall reaction during the discharge process is nickel oxyhydroxide plus the hydride of this metal mixture here producing nickel hydroxide plus the pure metal. And then during the recharge process, again the metal hydride is formed. Okay. Next we come to one of the most popular types of batteries that are being used in today's world, which is the lithium ion battery. Okay. The advantages of lithium ion battery is it is using lithium, which is the lightest metal element in the world. Okay, so after hydrogen we have lithium. Okay, so that improves the weight aspect of these batteries significantly. Okay, so these batteries operate by the movement of positive lithium ions between the positive and the negative electrode. So here, unlike the other cases, the metal ion itself is small enough that it can move easily through the electrolytic substance. So the lithium ion is directly moving during the discharge cycle from the negative electrode side to the positive electrode side. Okay, so lithium is basically dissociating on the negative electrode side during the discharge process, and then recombining with the electron in the positive electrode side to produce pure lithium. Okay, so that's the basic idea. And during the recharge process, the direction of the movement of lithium ion is opposite. Okay. Now here, the negative electrode is typically made of carbon. So we will see how the reaction actually works. And the positive electrode is made up of a lithium metal oxide, an oxide of a lithium with some metal added to it. Okay. So the negative electrode is made of carbon. The positive electrode is a lithium metal oxide. So the positive electrode material are lithium metal oxides like lithium cobalt dioxide, lithium nickel dioxide, lithium manganese oxide, etc. So this is what the material of the negative electrode is. Okay, positive electrode is. The negative electrode is usually made of graphite and some other carbon material that can accept the lithium ions to produce lithium carbides. So that is why we are using carbon as the negative electrode, because lithium metal can react with carbon to produce lithium carbide molecules, and this gets stuck on the electrode surface. Okay. So here what is happening then is that during the discharge process, the lithium carbide is dissociating to produce the lithium ion, and the lithium ion is going this way to recombine with the electron to produce lithium metal oxide, whereas in the opposite side, the lithium metal oxide during the recharge process, the lithium from the lithium metal oxide is being dissociated and is going towards to reform the lithium metal carbide atoms, lithium carbide molecules. So the typical discharge reactions in the negative electrode side is LiXC6. So X is typically of 0.5. So this lithium carbide does not have a exact molecular formula. So it's around Li 0.5 C6. So every 6 atoms of carbon has 0.5 atoms of lithium. Okay, and this dissociates to form pure carbon, that is graphite, X moles of lithium plus ions and X moles of electron. This electron is moving to the external circuit during the discharge reaction. And in the positive electrode side, you have lithium 1 minus X cobalt oxide. Okay, so if X is 0.5 here, then 1 minus X here is also 0.5. If X is a different fraction, say 0.3, then this is Li 0.3 and this is Li 0.7. So basically, you are playing with 1 mole of methane, 1 mole of lithium. Part of the lithium is with the metal oxide and part of the lithium is in the carbide form. So for per mole, there is, let's say, a part of it, X part of it is with carbide and 1 minus X part of it is the lithium metal oxide. Okay. So during the discharge process, Li 1 minus X cobalt oxide is reacting with this X moles of lithium plus ions that is coming from the negative electrode side, and the X moles of electron that is coming from the external circuit recombining to form lithium cobalt dioxide. Okay, this can be any of these metal oxides as well. Okay, the same formula will apply. Okay, so there is certain material issues, some are more advantageous than others, so we will not go into those kinds of material details, but this is the basic half cell reactions for the negative electrode and the positive electrode. So the total reaction during the discharge is LiX(C6) plus Li1 minus X COO2 producing 6, so C plus LiCOO2. So hence during the discharge process, at the end of the discharge process, you will get pure carbon as the positive negative electrode and fully lithium cobalt oxide in the positive electrode. While in the recharge process, you are getting lithium carbide and lesser lithium in the mixed with the metal oxide system. Okay. The EMF of this lithium ion battery is 3.7 volts. So it's significantly higher than any of the other EMFs we have seen so far. And this, remember, lithium based batteries are in the higher end of the spectrum as we discussed earlier, because lithium is the lightest metal and it's also near the top of the left periodic table. So it's one of the main alkali metals, right? Lightest and strongest of the alkali metals present. Okay, and so hence you are getting a high EMF value. Okay, very high EMF values for these lithium ion batteries, and it also has a very high specific energy density of 190 watt hour per kg. So these are actual specific energy densities, which is 3 to 4 times that are found in lead oxide or nickel based battery systems. It also has a reasonably very high power density of 2000 watt per kg as peak power. Okay, remember that energy density and power density, there is a trade-off. So if you get a peak power of 2000 watt per kg, at that peak power value you won't get the same specific energy density as this one. Okay, but still you can get very high power densities along with high specific energy densities as well. Further, it is extremely stable. So it has a low self-discharge time. It's 3% per month only. So a new lithium-ion battery, well-designed one, can last you, can be switched off for over 1 or 2 months, and when it is turned back on, it will still have charge. So it has a very low self-discharge time and hence is a long-lasting. So even slow cycles it can handle. Okay, and it has very good cycle efficiency of 90% and above. So you are getting more than 90% of the energy back, that which you were originally putting in. It also has a wide operating temperature. So it can go from minus 25 degrees centigrade to plus 45 degrees centigrade, which is a range of most usual applications. So its operating temperature is also very good. Okay, and it has a cycle time of over 1000 cycles. Okay, so you also get a reasonably large cycle time for these systems. Okay. So, but remember, this is around 1000 cycles. Still, this kind of explains why your cell phones and your laptops batteries begin to go bad after 3 years, because 3 years is approximately 360 into 3, 1100 or 1200 days. So if you are charging your cell phones and laptops every day, it is going through one such cycle. So after 3 years, you expect those batteries to go away. Okay. So this is an important point, and recently, especially with the EV systems, we need battery lives that can last 8 to 9 years. So a significant improvement have been made specifically for EV based batteries, which are designed with good thermal management, good battery materials, that has significantly improved the cycle time of the lithium ion batteries that are present in the electric cars. Okay. There the cycle life can be significantly larger than this, and it can last 8 years or 9 years according to current manufacturing ratings. Okay. So in that case, you can have lithium ion batteries with much higher cycle life than 1000, maybe 4000, 5000, etc. Okay. Now the electrolyte material may be a liquid type or a gel polymer type. Okay. Usually water-free liquid electrolytes are used. usually a mixture of organic solvents and lithium salt is used. Okay, in lithium-ion batteries, we specifically avoid water. We use water-free liquid electrolytes, a mixture of organic solvents. So organic solvents are like hexane, butane, so all the organic liquids, and lithium salts. A popular salt is lithium phosphate fluoride, LiPF6, lithium phosphate fluoride salt. This is a popular salt. So this salt is dissolved in the organic solvent, and this mixture of organic solvents with lithium salt is used either in a liquid type or a gel polymer type medium. Okay. So it's commonly used in cell phones, laptops, electric vehicles, and grid energy storage. It has high energy storage ability, large power output, long cycle lives, long cycle times, good round trip efficiency. So lithium, so when you look at grid energy storage, lithium ions are becoming a battery of choice. And in electric vehicles, of course, lithium ion batteries are the only batteries which have the correct weight to energy and weight to power performance that can make it possible to run cars using batteries. Okay. And of course, it is used in cell phones and laptops, being the lightest battery with very good energy storage. It is absolutely indispensable for portable electronic devices like those, which are requiring reasonably high power output. The main sustainability issue for lithium is a rare earth element, and hence is not widely available at all. Okay. So there are sustainability concerns and concerns that lithium will eventually run out reasonably quickly because of the extensive utilization of lithium in today's world. Okay. So we require recycling and reuse of lithium from exhausted batteries, and hence it has relatively high material cost. Okay. We need to reuse and recycle lithium. Lithium is not easily available, so it has high costs, and it is also sensitive to geopolitical tensions. Okay. Another issue is the lithium mining process nowadays is still not very environment friendly. So lithium mining also has environment and sustainability concerns. Okay. So those are the aspects that that needs to be taken into account when we are looking at the sustainability issues of lithium ion batteries. But otherwise, in terms of performance, lithium ion batteries are extremely important for electric vehicles, for renewable grid storage, and for portable electronic devices. So one of the problems that we discussed for the lithium ion battery is the lithium is expensive and not easily available on Earth. Okay. So there is research ongoing to create alternatives to lithium ion batteries which do not require such expensive or hard to find materials. So one such battery is a sodium sulfur battery. Now this battery, we are switching to a different kind of a battery structure which is called a molten metal battery system. So here, till now we have looked into this. We have a solid anode, a solid cathode, and a liquid electrolyte. Now we will have a liquid metal based anode or negative electrode. Okay. So these are called molten metal battery systems, and they have higher operating temperature of 300 degrees centigrade. So instead of the anode being a solid metal and the reaction happening on the surface of the solid during the discharge process, the metallic anode is or metallic electron donor during the recharge process is a molten metal which is kept in a container, okay, to which the electrolyte is transferring ions to and fro, okay, and the temperature of the entire system is high, it is above 300 degrees centigrade. So these are hot systems. You have to give heat to it, or the heat that is generated during the generation of energy from these batteries can be reused to give this heat. Okay. So one such molten metal battery system, there are several types, is the sodium sulfur battery. So here the metal is, the molten metal in use is sodium. So again, sodium is a periodic table element which has low in weights and has good characteristics, making it so you can get high EMFs and high energy densities. Just somewhat heavier than lithium, of course, but still the next best choice after lithium. Okay. The problem with sodium is because sodium ion, sodium is a larger atom, it is not easily transportable through the electrolyte medium. Okay. So that's why we are using a molten metal system, because heating and liquefying the sodium increase the mobility of the sodium ions, and that makes the reactions work. Okay. Here during the discharge process, the negative electrode reaction is just 2 atoms of sodium producing 2 atoms of positive sodium ion and 2 electrons, and the electron is going to the external circuit. While the positive electrode reaction is 2 atoms of sodium plus X atoms of sulfur plus 2 atoms of electron producing sodium sulfide salts. Okay, sodium sulfide compound. So Na2SX. Okay, where X can be 3 to 5. So it can be 2 atoms of sodium with 2 atoms of sulfur with 2 electrons coming from the external circuit to form Na2S2, or it can be Na2S3, or it can be Na2S5, sodium sulfides, different types of sodium sulfides. Okay. So here basically your electron acceptor during the recharge process, or the positive electrode is sulfur and the negative electrode is sodium, and both of them are in molten condition. Okay. So the 300 degrees centigrade is above the melting point of both sodium and sulfur, which makes this reaction possible. So this is the schematic of the battery system. So this red zone is where the liquid sodium is stored. Okay, so this is the liquid sodium is stored in this red zone, and this yellow is where the liquid sulfur is kept. Okay, so these are, and in between there is a beta alumina separator. Okay, so this separator, which is a refractory material between the molten sodium and sulfur, so this can withstand the heat and remain in solid form, and hence can separate out the two molten electrodes from each other. Okay, and you have two basically electrical contacts contacting the sulfur container here and the sodium container here. Electrons are coming out of the sodium from sodium, going to the external circuit and coming back into and reaching the sulfur through this electrical contact here. Okay. The EMF available is around 2 volts, relatively good, and the specific energy density is 200 watt-hour per kg, which is almost as good, even, and is if not better than that of lithium ion battery. So you have very good energy densities even though the EMF is low. Okay. And it has a very high cycle time of 10,000. So once a sodium sulfur battery is established, it can run for a very long period of time. Cycle efficiency is not that great, around 80%, because a lot of the energy is also wasted in heat. But the advantage is both sodium, sulfur and alumina are inexpensive and widely available. Okay, so the material costs are significantly low. Disadvantages requires thermal management to keep the operating temperature fixed and to prevent overheating. So remember, it's already running hot, and when you require a lot of power, the reactions generate even more heat due to irreversibility associated with it. So then there is a real chance that the system will become overheated and there can be fire hazards or explosion hazards. So it requires a good thermal management system to keep the operating temperature at the optimum point. And it can be used for large scale stationary power storage and grid storage applications. So the system is robust and it works well with stationary power systems, you can build big facilities with good thermal management, and you can fill it with a large amount of molten sodium, molten sulfur, and inexpensive beta aluminium, and hence store a large amount of energy. So there are already two working models, like 350 megawatt energy storage facility with sodium sulfide is established in UAE, and 1 gigawatt energy storage facility is already established in Mexico with sodium sulfide battery. So this is one system that is designed explicitly for renewable energy grid storage or distributed energy based storage systems. So today we will stop here. Till now we have discussed how to store electrical energy in various forms, whether it's transferring electrical energy to mechanical energy, transferring electrical energy to electrostatic potential energy, or transferring electrical energy to chemical energy in electrochemical energy in batteries. However, electricity is not the only form of energy we want to store. Many industries require heating systems and temperature gradients, and so we also want to store thermal energy, and we want to store temperature gradients effectively as well for those industries. So in the next class onwards, we will have a brief discussion on thermal storage methods and technologies. Okay. So thank you for listening, and hope you are having a good day, and see you in the next class.